So, welcome to the 11th lecture of number theory. So, last time we talked about the Diophantine approximation theorem, and we kind of proved it where we left out many technical details. And the last three lectures will be about algebraic points on the curve, algebraic torsion points, and complex multiplication. And maybe we actually can get to some applications in the up-to-date research where we use elliptic curves with complex multiplications. So we turn to the algebraic points. So consider the curve this curve. And let's say we want to compute the torsion points. Okay, it has discriminant 2 to the 12 times 11. We could now use Lutz-Nagel and our hands and compute all the torsion points, or use a computer and find out that those are torsion points. And we just now take for granted that there are all the torsion points as a black box. All rational torsion points. Yeah?
What exactly was our D there?
Ah, the discriminant. Where we, in Lutz-Nagel, where we have to check all the factors of D. So this would be now a pain in the ass because this has a lot of factors, but I just write it down anyway. So with a computer, we could check all the divisors here, check if we have a solution, and then we would get those points. But it's not important. This algorithm, we talked about it. What's now important is, so those are the rational torsion points. And yeah, well, the title of the book is Rational Points on Elliptic Curves. But now we want to find out what happens if we allow maybe larger fields here, not only Q, but maybe Q bar or something in between. So take a field that's slightly larger than Q. It's the number field where we adjoin square root of -2. So we have square root of -2 and all combinations between this and rational numbers. For example, in Q square root of 2, we have more torsion points. We have more points. No, what I... So that's what we take as a black box, that these torsion points that we or the computer found are actually all the rational points. But we can find more points over this field. For example, this one. And we can compute the double of this point with just our formulas, and we just have to be okay with the fact that there's a square root of -2 there. So we doubled the point, we have some denominators, and even though we won't prove it here or didn't prove it, we will also take as a black box that this is actually a point of infinite order. So we won't prove it, we will just take this statement . So what does it mean that it has infinite order? It means we can add it to itself and get new points all the time. So the curve y squared is equal to x cubed minus 4x squared plus 16 over q squared of -2 has infinitely many points. It has those points as torsion points, and it has infinitely many points, namely at least all the multiples of this. Maybe it has even more. But the interesting thing is that we only go one step away from Q. So Q is the rational numbers, and this is a very small number field since it has the smallest possible degree, only 2, and we get infinitely many points. So it makes sense to ask the question, how do algebraic points look in general? How do k rational points for k number field look like? And how do the torsion groups look like? And in order to do that, so you all had something like algebra where you talked about Galois extensions. Of Q. Well, what is a Galois extension? Basically, what you need is that if you have an element of the Galois group, the Galois group is an actual group. So the automorphisms of K over Q land in K. So, which means we can use the Galois group. So if K is a Galois extension of Q, then we can take elements in the Galois group and throw them onto points with coefficients in this field. So let's just, then we can do things. Namely, if we have a point on an elliptic curve where the coordinates of the point are in the field K, then we can just take, and we have an element in the Galois group, then we're able to do this. So this is our definition just of what happens when we let elements of the Galois group act on elements in E of K, namely those points. We just take the sigma and apply it to the coordinates And of course we want this because then everything is nice. And we have a proposition which basically says everything works out well. And I will not prove it. I think in the book it's partly proved, but it's more important that we just have it. So we have an elliptic curve. An elliptic curve with coefficients in Q, and we have a Galois extension of Q. Then we have some properties, and you should remark here that K here can also be something infinite, of infinite degree as long as it's Galois. But in practice, we will just care about number fields that are Galois. So usually we just take some number field, and then if it's not Galois, we just add some other things to it, and then it's Galois, and then we can play around with it. So what is true then? E of K is a subgroup of E of C. So this means that if we have a point on the curve and an element of the Galois group, then sigma of this point is again on the curve. And this is basically true because sigma fixes everything that's in Q, and the elliptic curve has coefficients in Q. So it doesn't change the curve, it just changes the point, and the fact that the point was on the curve is still true afterwards. I think this is a bit just of calculations. Then if we have a point on the curve and two elements of the Galois group, I'm not very good at writing tau. Maybe like this. So whenever you see something that looks like some T that's a bit curly and it's an element of the Galois group, then it's usually tau, and I'm not very able to draw it nicely. Okay, so these two elements of the Galois group. And then this is just this. I think you can also prove this by just writing down the equations. And this is just a bit technical. And it also works well with the addition on the curve. And this also basically comes from the fact that the addition and also taking the inverse of points on the curve is defined by some rational functions. And again, sigma fixes everything that's in Q, so everything works out. And this is, of course, again, then on the curve, and it works well with taking the inverse and adding points. So the proposition basically says that the group of k rational points on an elliptic curve and automorphisms in the Galois group, they work well together. And that's very nice. And we can do a lot of things with that fact. And yeah, we will not prove anything of that. You can look in the book if you want to see the proofs. Yeah?
Sigma p is what?
Oh, there is a minus. So you can take the minus out. Yeah. So now we want to find out about torsion points, or maybe the group of an elliptic curve. Where the torsion points have coordinates in C. Or as we will see in Q bar, because I think I sometimes dropped the remark that torsion points have algebraic coordinates, and that this is clear because they are defined by algebraic equations, but we have never proved this, so you you should maybe erase that sentence from all the videos before. But today we will probably like half prove it, that they're all roots of algebraic polynomials. At least we will give an idea of the proof. Or maybe, yeah, we will see. Okay, but we also want to find out about the structure of the torsion points, the group of the torsion points with coordinates in C, even though we later will see that the coordinates are all in Q bar. So in Julian's lecture, where he talked about elliptic curves over C, we learned that an elliptic curve over C is basically a lattice. So a lattice is maybe in some coordinate system, maybe some, yeah, I cannot draw. Maybe like this. And if we write it down, then it's C modulo L, because now probably we took lambda, but lambda is also not so easy to draw. So C are the rational numbers, L is a lattice, and the lattice is basically this fence here. So L you'd write it like this. Or maybe M and W are also not good characters that work together. Naja. Okay, so a lattice is, yeah, kind of like a vector space. We have two base vectors that give us the direction, and then we have M1 and M2 integers, so we can go in any direction. And now if we consider the end torsion in that letters in the C modulo L. Let me think how I write that down. So if we look at this, what is this? A1 and A2, first we can maybe just see them as integers. And W1, W2 are the base vectors of our lattice. And if we divide here by n, we just get the n torsion points, because if let's have this example, 3 over 5 times W1 plus 2 over 5 times W2, then we multiply by 5, and in here multiplying by some number is just multiplying the actual number, so then we would get a 3W1 plus 2W2, which is in the lattice, so in here it's the identity element. And of course, instead of taking 3 and 2, we could also take 3 and 2 in Z mod NZ, so take plus 5 times anything, and here also 5 times anything, because later in C modulo L, it would not make a difference if we have some more copies of some more, if we add W1 or W2 some more times. So this is how the torsion points look like, and what is the structure of this? It's basically only this A1 and A2, which are independent from each other. So the torsion subgroup with coordinates where we allow anything in Z is just isomorphic to Z mod NZ cross Z mod NZ. Let me formulate that a bit more clearly. Do I have a good formulation here? Yeah. Okay, so maybe this makes it a bit more clear. Here we are in the complex numbers modulo the lattice. So this is not necessarily an integer, and if it's an integer, then this is and this too is an integer, then this is an element of the lattice. So it's 0 or the identity, and this happens exactly if A1 and A2 are 0 here. So the n torsion subgroup of E of C is isomorphic to Z mod NZ cross Z mod NZ. This is a proposition. Okay, so this means the n torsion points, and this means with coordinates in the complex numbers. And as an exercise, you will get what are the possible n torsion groups if we put a number field here. And I will probably also find something how to relate this with ChatGPT. So you will maybe, if there's capacity, you can ask ChatGPT, what are the possible groups here? The answer will, with I think probability 95% will be wrong, but plausible. And you will have to explain why it's wrong and why it's plausible. Yeah, that's what I also always find so fascinating, that if you give the answers to some maybe person who does not number theory but numerics, then they would think it's true. Okay. Okay. What you probably heard on Monday in the exercise lesson can also be transformed to elliptic curves. So in Q you can look at roots of unity. It's also a letter that's not so easy to draw. So let zeta be a root of unity. And then, well, basically the statement is Q adjoined this root of unity is an interesting object to study. And well, this root of unity is basically nothing else than the torsion points if you consider multiplication or raising to power in Q. So the same we can do on elliptic curves, but with those torsion points. The analog for elliptic curves would be yeah, we just define it in the proposition. So we have an elliptic curve with rational coefficients. Let E be an elliptic curve with rational coefficients. Then, as I said before, the torsion points have algebraic coordinates. So it cannot happen that, I don't know, pi, square root of pi, and then, yeah, I cannot just from the stand just think of a irrational transcendental point. So nothing with pi, for example, can be can appear as the coordinates of a torsion point. These are always algebraic numbers. Second, So if those are the torsion points, then we define Q, where we adjoin all the coordinates. And then this is a Galois extension. So, and remark that this doesn't hold for the points of infinite order. They can be crazy, but the torsion points always are algebraic numbers. So this, if you just look at one n, or several n at the same time, but only finitely many, then this is always a number field, because all the coordinates are algebraic numbers. So the degree is finite, and the degree of the field extension where you join all of them will also be finite. So this is a number field. A very interesting object to study, and I studied that in my PhD, is the union of all those for all n. Then this is not finite anymore. This is an infinite extension. It's a very large extension. And it's not abelian, which makes it, well, in the generic case, it's not abelian, which makes it very interesting to study. Okay, we are going to prove this. I will basically give two proofs. And the proof of the part one, I just start with the proof. So, proof. Okay. Okay, so just take some point on the curve. So with possible complex coordinates, but n torsion, and not the point at infinity. So we want to know if it's n torsion. So let me write it like, how can we tell if NP is the point at infinity? For n equal to 2, we just have a formula. Where we have the duplication formula, and then we want the denominator to be 0, and this means y has to be 0. We let E be defined in this long form. Doesn't matter which way of writing we take. So, okay, for the two torsion points, it's clear. So this is an algebraic. This is a polynomial with rational coefficients. We can multiply by the common denominator, and then we have a polynomial with integer coefficients. So two torsion points have integers, have algebraic coordinates. And yeah, it would be nice if we had for any n such a nice formula. But unfortunately, we have a formula that's like the x-coordinate of p is a polynomial in x and y over some other polynomial in x and y. And since we have x and y, there is no reason why this should be equivalent to some polynomial. But what we also have is this. If we have, so our point from the beginning, if we multiply it by n, then the x-coordinate of n times p and the x-coordinate of the inverse of n times p are the same, because inverse points have the same x-coordinate. And only the y-coordinates differ by minus. And this, yeah, that's where I said we will prove it kind of half. This you can use it to show that this is actually just a polynomial in x and not a polynomial in y. Oh, this is x times np, x of np. Wait. And we give those polynomials a name. Stehe ich auf dem Schlauch. Wie heißen die Buchstaben? Phi und Psi. Phi und Psi. Yeah. Okay. I think in the not in this Silverman book, but in the other one where it's a bit more detailed, he proves how the polynomials look like, and also some bounds on the coefficients, and they are actually useful to compute multiples of points. But yeah, it's pretty technical to actually compute them or prove how they look like. Yeah, yeah. And I think in the Silverman one, so in the arithmetic of elliptic curves, there's some exercise with some mistake in those polynomials, and I found that mistake and I wrote to Silverman, and in the next edition he wrote in the introduction, "Thank you, like 200 people," and I was also in there. Yeah, so yes. Okay, and this, yeah, well, now this basically finished the proof, because so this is an n torsion point if psi is 0. And yeah, those psi n are polynomials with integral coefficients. This is the definition of x being algebraic. And yes, if we have that x is already algebraic, then since y squared is x cubed plus ax squared plus bx plus c, then y is also algebraic. So we only have to check one of those, and then the other one follows immediately. But of course, if we can also find combinations of x and y where none of them are algebraic, but then they are not torsion points. Yeah, yeah, we will be able to prove B before the break. Okay, what else do we want to prove? We want to prove that this field extension is a Galois extension. Oh, I called this A and this one, so this is 2. So, as I said, what does Galois mean? It means we stay in our field. So we have to prove that if we have a field homomorphism from this, and K should be this QEN. So if we have a field homomorphism from K to C, we want sigma of K to be inside of K. Yeah. Okay, so let's take points and call them Pi. So those should now be all the torsion points. And yeah, I erased it, but before we theoretically proved this. This was the first proposition that sigma of the point at infinity is the point at infinity. And then the Pi are n torsion points, so point at infinity is n times Pi. And we showed that sigma of P plus Q is sigma of P plus sigma of Q. So we can take this n out, since this is sigma of Pi plus Pi plus Pi and so on. So this is sigma of Pi plus sigma of Pi n times. Okay, we use this proposition. This always confuses me, those sounds at all the even hours, or all the hours. Okay, so that means sigma of Pi is again a torsion point, an n torsion point. Yeah, which is basically what we wanted to show. So this sigma of Pi has coordinates some xj, yj for some other torsion point. And hence the coordinates of this are in the field K. So the sigma lands in K. So the x coordinate has to be in K, the y coordinate has to be in K. Therefore, sigma of K is inside of K. Yeah. So actually this would also prove the part 1, which we only almost proved, because well, this means that the sigmas just permutate finite number of pi's. So the this field QE of n is a number field, and this also, of course, means that well, this means that the degree of this whole thing is finite. This means that degree of the xi's and yi's are finite, and this is just the definition that they are algebraic numbers. Okay, let's take a break until 11:10.